Hi everyone, welcome. We're going to be going through an example problem of how to solve a differential equation involving a simple RL circuit. In our example, we're going to use a simple RL circuit, meaning we have a single resistor in series with an inductor, which is a solenoid or a coil of wire. And in our problem here, we're going to have an open circuit that at time zero is going to become closed, allowing current to flow. The goal of this is to first write but not solve the differential equation that we could solve for current as a function of time. And then we're actually going to get that current as a function of time by using calculus to solve the differential equation. So before we get into part A, we need to figure out how are we viewing this circuit, right? So let's think about what's happening here and what we might expect. So initially, before this switch is closed, there is no current anywhere because we have a broken loop, right? There's no current. And the key to these problems is to first and foremost go right to this inductor and think about what is the current at its initial state, meaning before you've made any changes. In this case, it would be zero current because the change would be to close the switch. And when you do so, the previous current that was going through the solenoid of zero is going to be the initial current when you throw the switch. The current at steady state through the solenoid is the other thing we can look at. And so what we do is model this solenoid as a wire. So if we replace this coil of wire, which is simply a wire, after all, it is a wire, then this would just be a single battery and a single resistor circuit. Again, this would just be a wire. So at steady state, we would expect the current to be epsilon over R. So if you think about a graph, when we close the switch, previously there was no current, and so our initial current would be zero as well. And then at steady state, when all the change has occurred, and this is now behaving as a wire, the current through the solenoid would end up being epsilon over R. And that would be the flat line steady state that we're going to approach with a natural exponential curve. Just like with RC circuits that had natural exponential curves, we can also piece together what the function would look like. And so with knowledge of the maximum value, in this case epsilon over R, and the fact that this is a growing natural exponential, and therefore we can use the format of a growth natural exponential, then we could piece together what will end up being our answer to part B, which is that current as a function of time. We just need to be able to derive it using calculus. This R over L coefficient is also something that we would have to identify, right? Because this should be 1 over the time constant. R over L is 1 over the time constant, 1 over tau. So that will come into play here on the next slide. So we're going to start to answer part A. And when we do that, we need to start with the loop rule. We're always going to start with the loop rule for this as a starting point. So we have the battery voltage. Since we're in between the initial current of 0 and the steady state current of epsilon over R, then there is going to be a current and therefore voltage drop across the resistor. And there still is going to be a changing current, which means there's still going to be a voltage. Once the current has reached its flat line constant, then it's no longer going to have a voltage. And wires don't have voltages, so this makes sense when it behaves ultimately like a wire. So for our differential equation, we're going to replace this VL with this term that has its differential. And this is going to be our answer to part A, which asks us to write but not solve a differential equation. If we were going to pursue solving this, or if we did want to try and get the time constant, then we would want to rearrange it into our special format where the variable in question, in this case current, is its own term. So to do that, we have to divide all three of these terms by R. And now this is going to be our special form, and special because this allows for us to easily solve the differential equation using the U substitution that we did with the RC circuits. I'm about to do that in the next slide. And we also know that whatever the coefficient is in front of our differential is the time constant. And that's going to fit nicely with our previous expression. Remember, the time constant is L over R. So if we look back at the previous slide, 1 over tau is going to be L over inverse of L over R, which is what you see here, right? It's 1 over tau, so that makes it its reciprocal. Right, and the reciprocal of L over R is the R over L. But let's go ahead and solve this for part B. It says use integral calculus to derive this, and we're going to go ahead and do that right now. So the first thing we're going to do is we can go ahead and solve it by separating di and dt. Or if it's in the format like we see here, where it's not that easy to just do that, then we can use a u substitution. The u substitution is always going to allow us to make that left side u, because we have it in that arranged format where I is its own term. And that allows us to then solve for di and replace that in terms of du. And now we have it in a more solvable format. This would be the same format that if it was in already, we could just go ahead and solve it. Since it wasn't already in this format, we could use a u substitution to make it into that format, where I would have been by itself on the left side of the equation. But since we had two terms on the left side of the equation, I and this epsilon over r, we can let that be u, and that will allow us to solve it in the same way. So now starting off with this equation, what we need to do first is we have to ideally separate and integrate this. So I need to get the u and the du on the same side, and then all the constants and dt on the other. So in doing that, I'm going to multiply by the reciprocal. This is why we have that reciprocal thing with the time constant that we end up with, like r over L times t, right? Because when we integrate both sides, you're going to get negative r over L t. On this side, when we integrate 1 over u with respect to u, then we get the natural log, right? Putting units on this, limits on this thing, we're going to go from 0 to time t. So from time 0 to some intermediate time t. It's not quite a steady state yet, so it's going to be at some time t. And then our initial and ending conditions for u, we'd have to leave as u naught and u for right now, and we'll sub back in for those later. As we just were talking about, that since r and L are constants and the integral of dt is just t, when we sub in t for that, we get negative r over L times t, and when we sub in 0 for t, we get 0. As also previously stated, the integral of 1 over u du is going to be the natural log of u minus then the natural log of u naught, which we can write in fractional form like you see up here. This allows us to multiply both sides by u naught and raise it to the power, use exponential to get rid of the natural log, and then we can multiply by u naught. And that's going to give us this expression. Now these are in blue because we need to now substitute out the u and the u naught with what we defined as u. So u, for example, is epsilon over r minus I. So we're going to substitute that in right there. U naught is at time 0 when there was no current through the inductor or through the circuit at all. And so then u naught would just be epsilon over r minus 0. So in substituting those in, we get this expression. Now we're pretty much done here, except we just got to solve this for I. And so once we solve this for I, we end up getting the exponential that we had expected in the previous two slides when we first were looking at this. I hope this helps, and let me know if you have any questions. Have a great day.